Now let us study how we can use determinants to find the solution of a system of linear equations. So as the name suggests, here we have a number of equations which are linear, that is of degree 1. Now here are some important terms before we go into the details. The first is whether the system is consistent or inconsistent. Now by consistent we mean that the system has some solution. Alright, so when a system has some solution, that system is said to be a consistent system. On the other hand, if there is no solution to the system, then we say that the system is inconsistent. And secondly, if the system is consistent, that is, if it has solution, then either it may be a unique solution or there might be infinitely many solutions. So based on this, now we will see the different types or different cases of the systems of solutions, system of equations, and we will see what are the conditions so that we come to know whether a system is either consistent or inconsistent, and if at all it is consistent, then whether the solution is unique or there are infinitely many solutions. Now let us move ahead and see the first category, that is called as the system of non-homogeneous linear equations. Now as an example, let us first see the case where we have two equations in two unknowns, that is x and y. So here we can see two equations written in general. Now by non-homogeneous we mean the constant terms in the two equations are not all zero, that is there is at least one non-zero constant term in the two equations. Alright, now to solve these equations, first of all what do we do is we first find out a determinant delta given by the coefficients of variables x and y. So you see the coefficients of x are a1, a2 and coefficients of y are b1, b2. So if we make a coefficient of them, we will have a1, b1, a2, b2. Alright, then we find a coefficient denoted as delta x, which is formed by replacing the coefficients of first column, that is the coefficients of x which we have written in the previous determinant delta, by the constant terms. So that means we have to replace a1, a2 by c1, c2. So therefore now the delta x will become c1, c2 column wise, and the other column remains same as in delta. And similarly we also write delta y. Now here the coefficients of x will remain unchanged, whereas coefficients of y will change to c1, c2 in the determinant. So instead of b1, b2 we now write c1, c2. And next, now we have the formula to get x as delta x upon delta, and y is given by delta y upon delta. Now of course this is applicable provided the denominator, which is delta, is non-zero. Only then we will get a specific solution. Alright, now this is also called as we know, it is called as the Cramer's rule. Alright, so we are familiar with this process to find out the solution of this system of two equations in two unknowns. Alright, now let us move ahead. Now like we have two equations in two unknowns, similarly we can extend it, and here is an example of three equations in three unknowns. Once again this is a non-homogeneous system, that is at least one of the constant terms d1, d2, d3 should be non-zero, that is all of them cannot be zero. Alright, so in this case also we find out x, y and z on similar lines as we have seen earlier, with the assumption that delta is not zero. Now moving on, we have a different type, that is here we have now three equations but in two unknowns only, and we have to find out whether this set of three equations together has any common solution or not. and if it has, then what is the condition based on which we can find that out. Now if we think closely, for two unknowns we basically need only two equations, if at all there is a solution to that particular pair of equations. So that means if we find out some solution xy which satisfies the first two equations, that solution also must satisfy the third equation, so that we can say that all the three equations together have a common solution. So how do we know whether this particular set of three equations has a common solution? So for that we have a simple condition in terms of determinants, that is, we have to create a determinant using the coefficients of x, y and the constant term. So that means here we have a1, b1, c1, a2, b2, c2 and a3, b3, c3. Now if the system of three equations is consistent, that is, if it is supposed to have a common solution, then we must have this determinant equal to 0. So therefore consistency of these three equations implies that this particular determinant denoted here should be equal to 0. But it should be remembered that the converse is not necessarily true, that is, if a determinant is 0, then it does not mean that the system has a unique solution, that is, the determinant equal to 0 does not guarantee the consistency. But if the equations are consistent, then it always means that the determinant is equal to 0. Alright, now let us go ahead to study the system of what is called as homogeneous linear equations. Now here homogeneous means the constant term must be 0 in all the equations. So here we have two examples, that is two sets of equations. First is a set of two equations in two unknowns, and the other one is a set of three equations in three unknowns. Now let us concentrate on the first set, and we can extend the analogy similarly to the other set also. Now let us look closely at these two equations. Since the constant term is 0 in both, we can readily see that if we put x equal to 0 and y equal to 0 in the two equations, they will always satisfy the two equations because the right hand side will be obtained as 0. So that means x equal to 0 and y equal to 0 is always going to be one solution of this particular system of equations, and this solution is called as the trivial solution. Trivial means that it is just obvious, or it is a default solution which will always be there. Okay. Now apart from this, now we want to see, is it possible that this system has any other solution also apart from the trivial solution? Now if we consider the determinant formed by the coefficients, that is, say a1, b1 and a2, b2. So these are the coefficients of x and y. Now let's assume that a case where this determinant turns out to be 0. That is, if we take an example that, say, first equation is x plus y equal to 0 and second equation is 2x plus 2y is equal to 0. Now here we will observe that if we form the coefficients determinant, that is 1, 1, 2, 2, obviously both the cross multiplications are going to give us 2, so therefore that determinant is going to be equal to 0. Now what does this mean is, if we divide second equation by 2, we are going to get back the first equation, isn't it? So that means these two equations are not really two different equations but one and the same equation, which is nothing but, say, x plus y equal to 0. And now if we have just one equation in two unknowns x plus y, it is not difficult to conclude that there will be countless pairs of x and y which satisfy the given equation. That is, say for example, I can put x equal to 1 and y equal to -1, which will satisfy the equation x plus y equal to 0. or we may put x equal to 2 and y equal to -2, and so on. You will get countless pairs. So what does it mean is, if this particular determinant of coefficients is 0, then this system will have infinitely many solutions apart from the trivial solution. On the other hand, if the determinant is not equal to 0, then trivial solution is the only solution. So in that case we say that the system has a unique solution which is a trivial solution. But if determinant is 0, then the system has infinitely many solutions, which obviously includes the trivial solution also. Alright. Now the same analogy will apply to the system of 3 homogeneous linear equations also. Now based on this, let us summarize the overall picture in a kind of a tree diagram, so that we'll get a snapshot of all the concepts and conditions together. Now on the next slide we have that particular diagram. Just a moment, it's taking some time to load. Alright, now here we see the summary of solving a system of linear equations. On high level we have two categories, that is, on the left we have non-homogeneous equations, which we denote symbolically as a into x is equal to b. So where a stands for the coefficients of the variables, x stands for the variable themselves, and b stands for the constants in the equations. Now within this we have two cases, that is, if the delta is not equal to 0, that is a determinant of coefficients is not equal to 0, then the system is consistent and it has a unique solution. But on the other hand, if delta is equal to 0, there are two cases. If all of the three determinants, that is delta x, delta y and delta z, are 0, then the system is still consistent but it will have infinitely many solutions. Whereas if at least one of the three determinants, that is delta x, delta y and delta z, is 0, then it would mean that the system is inconsistent, and by inconsistent it means there is no solution to the system. Alright, so that is about the non-homogeneous equations. Now on the right hand side we have homogeneous equations, where we denote symbolically as ax equal to 0, that is, we have the constant terms as 0 in all the equations. Now in this there are again two cases, that is, if delta is not equal to 0, then the system has only trivial solution, and by trivial solution we know that it is a solution where the value of all the variables x, y, z, whatever, are all 0. That is called as a trivial, or the default solution. On the other hand, if delta is equal to 0, then the system has infinitely many solutions, including the trivial solution. Alright, so just to reiterate, the homogeneous system is always a consistent system because it always has at least the trivial solution. So that is an important point to keep in mind. Now based on this we will solve few examples.